carry on our discussion over the continuous time random variables. So what we did last time, we kind of defined that, okay, like we kind of think about the different kind of situations in which the randomness kind of arises in continuous time, and hence there is a need, so there is a need to represent that randomness through a continuous time random variable that, unlike the discrete time random variable, takes the values in an interval actually. So we defined the PDF, the probability density function, the cumulative distribution function for the continuous time random variable, and we defined, and we ended our discussion by defining the expectation for a continuous time random variable by defining it as an integral from minus infinity to infinity of x times f of x dx actually, where fx of x is the PDF. So this is the probability density function of x actually. Okay, so this is where we ended our last discussion. So what I would like to do today is that I would like to kind of generalize this notion, and I would like to compute what you call the expectation of a real valued function of x actually. Okay, so I want to compute the expectation of the g of x, where g is a real valued function. We kind of have already, I mean, if you remember, if x was a discrete random variable taking values say x2 and so on and so forth, then the expectation of g of x was like having a sum that goes from I equal to 1 to infinity, evaluating the g at each of the xi and multiply it with the probabilities of xi actually. Okay, so we kind of proved this result. So from this intuition, we can have a similar, so if this is the case in discrete time case, then you can already kind of guess actually that what would be the situation in case of the continuous time. Then in continuous time, it is going to be the sum is going to be kind of replaced by integral, multiplying the g of x. There you have this discrete PDF. Here you're going to have this fx of x and integrate everything over the d of x actually. Okay, so if you want to compute the expectation of some function of the random variable x whose PDF is fx, then expectation of g of x is really this integral actually. So I would like to prove this proposition. But before proving this proposition, I would like to prove a lemma first, and then I'll get to the proof of this proposition. So here's a interesting lemma, a simple interesting lemma that goes like this. So it says that if y is a non-negative random variable, so it's kind of a random variable that all of whose values are bigger than or equal to 0, then expectation of y, okay, can also be computed. So one way to compute the expectation of x is this formula, but you can also compute it by integrating from say 0 to infinity the PDF of integrating the probabilities of y being bigger than or equal to y dy. Okay, so this is an alternate formula for computing the expectation of a random variable, y actually, which is non-negative. So what you do, you compute the probability y bigger than y and integrate it from 0 to infinity, so that would give you the expectation of such kind of random variables. So here's a really sharp proof of it. It's a nice small result. Okay. So in order to prove the identity, let's take this side of the integral and try to show that it's equal to the expectation. So here's the thing, let's start with 0 to infinity, probability that y is bigger than y. Let's integrate it with respect to dy. Okay. Now, how to compute the integrals of a continuous time random variable? Probabilities of continuous time random variables. We know that for computing the probabilities of continuous time random variables, you need to write your probability in the terms of the integrals actually. So what would be the integral that represents it? This is 0 to infinity, and this goes from y to positive infinity. And how can I compute this integral? By integrating the PDF of the y, let's give it a name fy, okay, evaluated at any random variable x, dx actually. So this x is a dummy random variable of the integration, and dy. So what I just simply did, I just substituted the value of probability y bigger than or equal to 1. Okay. Now, can I integrate a function, this unknown function with respect to x? With respect to x, the answer is no. I mean, until and unless I can't know this function, I can't integrate it actually. So what should be done? So the trick that is going to work out is to do the change in the order of integration. In other words, change this integral, rather than computing the dx dy, let's compute the dy dx. But if you switch dx and dy, then you need to change the limits of the integral actually. So in order to make sense of it, let's try to draw the function that these limits represent. So what we know about x, so we know about x goes from y to positive infinity, while the y goes from 0 to positive infinity. Okay. So y is 0 to positive infinity, so that means that we are only talking about these two quadrants. Okay. So how can I plot this region? So y equal to x, so let's plot the endpoint. So what will be y equal to x? So the y equal to x is this line that really bisects the first quadrant. So this is really y equal to x. And what is the region that represents y less than x actually? Okay, so y less than x. So if I, for example, choose a point on the line, so this would be y equal to x. But if I choose a point here, so here you can see that, okay, the x is smaller, but the y is bigger actually. The y is bigger than or equal to x. So y smaller than x is really this region, this entire region actually. Okay, so we're talking about this region. Okay, and how the limits are going in this region, and currently that x starts from y and goes forever, while y starts from 0 and goes forever actually. Now if you want to change the order of the integration, okay, so if I want to write this integral as, say, integral, say, dy dx, then I need to put the limit on y actually. So what would be the limits on the y? So I mean, you can see that in this region y always starts from 0 and goes up to this line. So it starts from 0, goes up to this line. Starts from 0, goes up to this line. So it starts from 0 and goes up to this line, and what is the value of y here? So the value of y is x. And how about x? So the x in this region starts from 0 and goes on forever. So 0 to infinity. And just put the integrand f of x. Okay. Now this integral is with respect to y, while this function is the function of x. So I can pull this integral out of, pull this integrand out of integral actually. So I can take this out. So if I'll take this out, how is it going to look like? So it's going to be 0 to infinity fy of x and the integral from 0 to x dx and dy. Oh, sorry, dy and dx. So what would be the integral of dy 0 to infinity fy of x? So it's going to be y, substitute the limit 0 to x dx. And what did you get? You get 0 to infinity, you substitute the limit, you're going to get x fy of y and fy of x and dx. Now what is this thing? I mean, if you see, this is nothing but the precise definition of the expectation of y. Okay? There is no need to start from minus infinity because y is non-negative, so it always starts from 0. Okay? This is what the definition of expectation of y. So we started from the integral and simplified it and got this expectation of y. So I hope that, this proof makes sense to you. Now, I would like to write this identity. So this is really what we call the integral from 0 to infinity of the probability of y bigger than y dy. Okay, and it's equal to the expectation of y. So this is what the identity that we have proved. So I want to use this identity now to prove this result. Okay. I'll prove this result for the case when for the case when g is non-negative. In other words, g of x is non-negative. This is sufficient to prove because the rest of the functions, I mean, if you take a general function, you can write it in the terms of the positive part of it and negative part of it. So both are the non-negative. Okay, so since you can write a generic function in the terms of positive part and negative part, and both are non-negative, so, and I mean, if you want to recall the definition of positive part, so x plus is x when x is non-negative and equal to 0 when x is negative, while x minus is equal to negative x when x minus is x. No, x minus is 0 when x is non-negative, and it's equal to x when x is negative actually. Okay. It's equal to, I think, minus x if x is negative. So using these two definitions, every g can be written in the terms of these two non-negative functions actually. So since both of the functions are non-negative, and I proved this result for non-negative functions, so you can easily drive this result for a more generic real valued function actually. So let's do, let's assume that g of x is non-negative actually. Okay, so we can talk more about it later. Alright. So now let's take, say, let's give this g of x name. So g of x, g of capital X name y. And I want to compute what the expectation of y. Okay? And by this theorem I can say that this is equal to 0 to infinity. Okay? 0 to infinity probability of y being bigger than y. So this is what we know from this probability. Okay? And obviously dy. So if I substitute the value of it, okay, so I can say that this would be 0 to infinity. So this would be the integral, okay, from y on this region on x such that, okay, so if, for example, if I write this integral with respect to x and this y is really g of x, then integrate the PDF of the y, in other words the g of x, phi of x. Okay. Fx of x on the region what? Region on such x where the g of x is bigger than y. Okay, where the g of x is bigger than y. So what I just did, I just substituted the value of the probability y bigger than or equal to x. So y is what is a g of x. So how can I compute this integral? So I can compute this integral by integrating the PDF, because this is an expression in the terms of the x actually. So I can do what? In order to compute this integral, I can say that, okay, let's integrate the PDF of the random variable x onto those points where the g of x is bigger than or equal to 1. Okay, so in other words, I'm integrating over those regions where this constraint g of x bigger than y is satisfied actually. Okay, this is what it. So what we can do now, we can play the same trick, okay, of changing the order of the limit. Okay, so let's change the order of the limit. So in order to change the order of the limit, you need to see that, okay, my g sits between where to where? So my x sits between my g of x and x between g to say positive infinity, while the y goes from 0 to positive infinity. Okay. So if you want to plot it, say imagine g is some kind of this function. Okay. And you are talking about this region, the same as previous one actually. Okay. So what you're going to do, you're going to change the order of integration. You will say that, okay, you have this dy dx, where the y goes from where to where? Y goes from 0 up to the function x actually. So you say that 0 to g of x. So instead of line, now you have a curve actually. और कोई फर्क नहीं है दोनों में. While the x goes from 0 always to infinity. Okay. 0 to infinity. This is what it is going to be. And then you have what do you call fx of x. Okay. Now the same case, the fx of x is a function that depends on x, but you are integrating with respect to y, so you can pull this out of integral. So when you're going to pull this out of integral, you're going to have 0 to infinity fx of x, बाकी क्या बचेगा? 0 to g of x dy. So integrate dy, you're going to get y, and then substitute the limit, so you're going to get g of x minus 0, so you're going to have g of x and dx. So you have it. So from where we started, from here we started, and we ended up at this formula. Okay. We proved it at least in the case that when g is a non-negative function actually. Okay. For more generic function, as I said, that any real valued function can be written as the difference of a positive part of it and negative part of it. And this positive part and negative part both are non-negative functions actually. And for non-negative, this identity is valid actually. So if this identity is valid for g plus and g minus, so you can easily drag that it's also valid for g of x. Okay, so do it for yourself. Anyway, ठीक है जी. So इस result का फायदा क्या है? So what is the benefit of having this result? That if you want to compute the expectation of, for example, sin x, then it's easy. So what you need to do, just multiply sin x with the PDF and integrate. And whatever answer comes is going to be the integral of, is going to be the expectation of, what you call the sin x. Okay. So this is what really is the key thing. And you will see that this lemma is going to help us in many such situations actually. Okay. Let's try to use this lemma to solve some interesting problems. Okay. So here's an interesting problem. Here's an interesting example. Example 2c. So what does this example say? This says that imagine you have a stick. आपके पास एक stick है unit length की. ठीक है? So imagine that this length is 0 to 1. ठीक है? And you choose randomly a point on this stick actually. ठीक है? फर्ज कर दें आपने एक point जो है randomly choose किया है on this stick and you colored it actually. ठीक है? Then you broke this stick into the two pieces. For example, आपने एक length ली, say u, and you broke it. अब मैंने इसको दो हिस्सों में तोड़ दिया. एक हिस्सा जो है इसकी लेंथ है u and इसकी लेंथ है 1 minus u. So in this given situation, this chosen point, ये जो colored point है हमने जो किया है, ठीक है, choose किया है point, this lies in 1 minus u part. ठीक है. मगर ये जो break करना था, I could have also broken this, say for example here actually. ऐसा भी तो कर सकता ना कि मैं इसको यहाँ से तोड़ दूँ और ये जो u है that contains the colored point और जो दूसरा हिस्सा है 1 minus u that does not contain the color points. ठीक है? So अगर आप एक stick लें, उस पर एक point choose करें और फिर उस stick को break करें, तो फिर दो possibilities हो सकती हैं. या और break करें और एक stick का part लें कि जिसकी length u हो. अब दो possibilities हैं. वो जो आपका chosen point था, your chosen point is going to be in u or not in u. ठीक है? या तो u में होगा या तो 1 minus u में होगा. ठीक है? अब हमें मालूम क्या करना है? हमें वो एवरेज आप हमें बताएं क्या जी, क्या एक्सपेक्टेड लेंथ होनी चाहिए, ठीक है, इस पार्ट u की, so that कि ये पॉइंट इनसाइड u. So on average मैं कहां से रैंडम